All right, so our final example that I'm going to do for mass conservation is one that we'll come back to later in the context of conservation of angular momentum. So this is a rotating sprinkler. So the idea is I've got, I don't know, like an old school sprinkler that has sort of two exits that are spraying water out of them, but the head is free to rotate. So let's suppose that the head rotates at angular frequency omega, and that it's fed from the bottom through an inlet that has a total flow rate of 1 liter per second. And then there's a specified outlet area on the sprinkler head. So there's two sprinkler heads that are symmetrically opposed to one another, that each have a specified outlet area of 30 millimeters squared each. So the problem is to determine the velocity of the water that's leaving relative to the nozzle and relative to the ground. So like an observer on the ground sees one velocity, but an observer that's stationed on top of the nozzle sees a different velocity. What are those two velocities? What I'm going to do is I'm going to choose a control volume, and I need to be careful because at least our boundaries are moving. So I need to specify how our control volume moves as well. So I'm going to choose a control volume in this case that moves at the same angular rate as the nozzle itself. So our control volume moves with the nozzle, which again is not the same as the fluid because the fluid is going to be flowing through some of those boundaries. So if I write conservation of mass, by performing the integrals over our control volume, the Reynolds transport theorem would say that, zero, so the rate of change of mass of the material, is zero, which equals the rate of change of mass in our control volume plus the rate of, that should be a CS, the rate that, mass flows out of our boundaries or in and out of our boundaries. So that's a control surface integral over rho times the relative velocity dotted with n integrated over the surface. That first integral is certainly zero because at least, the volume of our control volume is not changing. Even the way that we defined it. It moves with the nozzle, but that volume, the total volume contained in the nozzle, doesn't change. So in this case, there are three total inlet/outlets. So there's one inlet coming from the bottom, and there are two outlets. So let's write out each one of those integrals separately. Zero equals the integral over, let's say, the inlet of rho times v, the relative velocity dotted with n. In this case, the relative velocity is just the velocity of the fluid because at least at the inlet, our control volume wouldn't be moving even if I, had it attached to the sprinkler because that's on sort of an axis. So that integral is easy to perform. The v dot n in that case is just minus the inlet velocity. Since density is constant for a liquid, that integral just amounts to essentially the flow rate coming in through the inlet. So rho times minus q, where q is the volumetric flow rate, would be the value of that integral. And then the other integrals we still have to do at the outlet, at the two outlets. So the integral over surface 1 would be rho plus v times plus the relative velocity, because the relative velocity going out is aligned with the outward unit normal dA. And then there's another integral that's identical to that corresponds to the second outlet. So I'm going to take this opportunity to move the rho times q over to the other side of the equation so that it, forms a positive sign. So rho times q would then equal 2 times the value of either one of those integrals, since they're identical integrals. And in this case, I basically, if the velocity is uniform over the exit, that I can just evaluate that integral directly as, the mass flow out, which is rho times VR, the relative velocity, times the area at the exit. So I can invert that and solve for the relative velocity at the exit, which would be q divided by 2 times the area of each exit. So that's actually the relative velocity. So that's like the velocity that the fluid would appear to come out of the nozzle if you were, attached to the nozzle, or in a coordinate system attached to the nozzle. So in other words, the relative velocity is defined as the actual fluid velocity minus the velocity of our control volume. If we wanted to find out the volume or the velocity of our fluid in a coordinate system fixed to the ground, what we'd have to do is take our relative velocity and add the velocity of our control volume to that. So the way that I've drawn the picture, the velocity of our control volume is to the left. So that's with a minus sign. So minus the radius at the location of the outlet times the rotation rate omega. So minus r omega is the velocity of our control volume. And so if I add that to our relative velocity, you can find the velocity relative to an observer on the ground. So I can evaluate that for you now. So the relative speed would just be q divided by 2 times the area at the exit. So for a 1 liter per second flow rate, converting that to SI units by multiplying by e to the minus 3 meter cubed per liter, then divide by 2 times the area at the exit, which is 30 millimeters squared. So a millimeter is 1 e to the minus 3 meters, and then I have to square that. Square that. And if you work that out, you find a number close to 16.7 meters per second. To work out the velocity in a ground-based coordinate system, you'd have to actually know what the value of the frequency of rotation is and the radius of the exit relative to the sprinkler's axis, which I actually didn't provide in the problem. So it actually depends on the rotation rate. So I won't bother evaluating that, but we have a formula for it.